So let's study Unit 2 of TensorFlow certification, and we are studying that from the candidate handbook. So going to the curriculum, this is Unit 2, where we build on top of the knowledge where from previous lecture, a simple neural network, and we see its important details in this unit. This forms the foundation of everything we'll learn. So build, compile models and everything. This we will see in one shot. Okay. So the links to the code you will find here on my GitHub repository. Unit number 2 is 2 dash unit number 2 you will find. Fuck. And here the first cell is this link. Okay, so these are the list of resources. I'm going to use this in lecture. Let's go through the code one by one. Okay. So we know these are the important libraries. TensorFlow is, what we are going to use. From the previous lecture, we know that if you want TensorFlow API, you do go to TensorFlow's API documentation. And if you want to go to Keras's documentation, which is what I recommend, because TensorFlow has absorbed Keras. Keras is a much easier to use library for neural network, and TensorFlow has absorbed it, and that's why there is this whole mess. I might have mentioned that TensorFlow Keras have this toxic marriage. TensorFlow is not that popular now. PyTorch is more popular, and whole this toxic mess. Keras was a library which tried to simplify. Then people were like, you know what, I want more control. So they also have another API. So it's a mess. But not going into the mess, going into only high level things. That is the Keras API documentation. And these two links together, we can write any code. Okay. So going to the code, we import the libraries TensorFlow and Pandas is another popular library, and NumPy is another popular library. Internally, they are all maths. It is a glorified calculator library. That is extremely true. Instead of saying instead of doing 1 plus 1 equal to 2, these are gonna do additions on millions and trillions of parameters. That is what is different about it. When we hear ChatGPT or any model has 50 billion parameters, when we do any operation, those many multiplications and additions we are doing. So we need to optimize them if we want to do it at that scale, right? Billions of parameter. TensorFlow is a specialized library for that. Okay. Going back into the internal details, what are neural networks? Neural networks are nothing but general purpose pattern extracting machines. Any Okay, general purpose, and there are a lot of important words here. General purpose. So this thing means they can extract patterns from data of any kind. So data could be the language we speak, or it could be nuclear fusion, which is happening on sun, and how to control the fusion plasma to get better electricity, or it could be how proteins come together to form, let's say, bacterias or viruses. General purpose means general purpose. It could be of scale of galaxies, data of galaxy formation, or it could be scale of quarks. So smallest to biggest, that's the as long as we convert it into data, this neural network can extract patterns from it. Then there is another corollary here. They can extract patterns even if the pattern is not there. So just because they are general purpose doesn't mean they are 100% accurate. There is another thing, it's a prediction based on statistics and probability. It doesn't really know. It is just a prediction. So that's why we can find places where it might be confident but it might be wrong. It might be overconfident. They can also extract a deeper pattern we don't even know. So, pay attention to this. We don't even know if the pattern extracted is the right pattern or not. Or it could be that that pattern is a deeper and subtle pattern we don't even know. So this is the mess I'm talking about in this neural network. So you have to ensure the network is learning, its is less, accuracy is high, and these are the things you will learn over time. But the basics are very simple. Basics are very simple. Concepts, just pay attention and you will definitely learn them. So any data to learn patterns from. TensorFlow has, I mentioned, has absorbed this library. So everything, most important things you will find under Keras. So tf.keras, and I mentioned its core API. So if I want layers, tf.keras.layers. If I want recurring layer, tf.keras.layers.lstm. If I want optimizers, it is tf.keras.optimizers, tf.keras.optimizers, and whatever is the optimizer name. So the pattern is very simple. It is very nicely organized. You will find it easier to guess. So data is called as data set. So tf.keras.datasets. If you want to know which data sets are present, go to this documentation, or you can always execute two functions, which are my favorite functions. This dir of something and vars of something. Dir will give you list of functions which can be called on that variable, and vars of something will give list of variables which are part of that variable. So if you do it on data sets, you will find it has MNIST, CIFR10, and some common data sets. And because neural network are general purpose pattern extracting machine, instead of this data, we can give it any data and it will still learn. Okay, that's how we are doing general purpose learning. So we load the data. It's the data in which patterns are present. And from that is what we are learning. This kind of learning depends on sheer data volume, not understanding. So that's why we need a lot more data to learn from, right? So checking into the model is simply a network. So now go to this rest of the links, which is TensorFlow Playground and NNSVG. So what is a neural network? It is list of things we called as neurons. Each neuron has a vector, okay, mathematical vector, and one bias value. That's all it is. Every neuron has a, sorry, each layer, this is wrong. Each, each, okay, this is correct, but each neuron has a weight vector. Okay, single vector and a single bias value. This is what we have. So we have that, and uh, every connection that neuron is making with input values. So what is it? We have, let's say, we are providing x1 and x2. The same input goes to all the neurons. Every neuron internally is a list of vectors, weights, and bias. Weight is same as the incoming values. So visually, you should be able to see that if there are three incoming connections, each neuron will have three weights associated with it. So you can see them in diagram. So this diagram, I'm going to do let's say size is 5 and there is this one. So here each neuron has a 4 lines connections, 5 lines coming to it. So each neuron has 5 weight values. So show bias unit is separate, and each value, if you find here in this, the each layer does a single operation. This is also, it might be complex, but don't get overwhelmed. Why? Because whatever we learn for a single neuron, the same operation happens in all other neurons, in all other extra layers we add. So everything is made up of a single neuron and neuron connecting to other neurons. Each neuron has list of weights, and we have many such neurons in the same layer. They have these weights and they all do a single operation called as dot product. What is a dot product? If you know Excel or if you know averages, dot product is a weighted sum of incoming values. A weighted sum, not just sum. If all values are equally important, then we don't have much info. But if one value is more important than other, then weighted sum is very important. So each value, according to its weightage, is added. So dot product does simple weighted sum, and as long as the weight value is the correct value, our network gives us the right answer. So this is a very weird way of looking at things. We take any data, okay, and we build a network, which could be any network. Different problems could have same network, and we give it a specific data, and we do something, and eventually we get an answer which has of correct combination of weights and biases for that configuration. We could do some changes and we could still get the right answer, or accurate enough answer. And this is neural networks. Okay, so model is a stack of layers. Each layer is list of neurons, and every neuron is a very simple vector of weights and a single value of bias, and we multiply input to the vector size of the whatever size we are giving. So check this code, tf.layers. Layer is this dense layer. It has 8 neurons and its input shape is 2. It has 8 neurons. So let me do this. And its input shape is 2. So every neuron has 2 incoming connections. So every neuron has 2 weights. Every neuron has 2 weights. Okay. So this is the weight vector and we have a bias value. And if you check this dir of this layer variable or vars of layer variable, you will find its internal details. Learn to ignore stuff with underscore. Okay. Whatever is underscore, it's a hidden thing. It's not that important. Whatever is non-hidden, that is important. And not all of it. So we need to develop an eye to check what is important. So what is important is these things which are headings of this notebook. They are the only things which are important. So we have data set, we have model, then we have error value. What is error value? Our model is any permutation combination of weights. And if we check the error of that permutation and combination, and error is 0, it means answer is correct because error is 0. So our problem is do error minimization or accuracy maximization, right? So just like no two people's brains are connected the same way, no means every brain is connected in different ways. Every network for different tasks could be connected in different ways, means it will have a different architecture. All we need to do, whatever it is do error minimization or accuracy maximization. So if we have a parameter weight which is positive and a very high value, if you have a parameter which is positive and very high value, it means that that thing is more important than others. So check here, this is thicker, so this is more important than others. And orange is negative, blue is positive. So for this solution, this is the kind of connectivity. Neuron number 2 has a more positive weightage to this value, whereas for this neuron, both of these values are negatively correlated. So the weighted sum we do gives us this very nice permutation and combination. A is connected to B in a positive way, or it is connected in a reverse way, or something is very less importance, or something is of very high importance. This thing you can find by this feature in this thing, which is edge width proportional to the edge width. edge opacity proportional to edge weights, and edge color also proportional to edge weights. With this, we can see, oh, for this neuron, this connection is not at all important. The only important connections are this neuron and this incoming layer. Whereas for this, it is different distribution. For this, it is different distribution. So in this way, we can kind of like always get different permutation and combination and visualize what it means for a trained neural network. So NNSVG and neural network playground are, that is why important uh, for websites for us to know. Okay, going to the code again. These are the only essential blocks. Trust me, even when we reach to the highest, which is like developing our own chat GPT, the code revolves around the same things. And the code is less than 200 lines. The example is micro GPT. There is a something called as micro GPT on GitHub, which is a level of a GPT code written in less than 200 lines or 300 lines. That's it. A GPT level code in 300 lines. The same permutation and combination of stuff we are learning in this notebook. So master this and you've mastered a very big chunk of AI. Models prediction, you need to know it. If you print the predictions, it comes some positive or negative value. It could be more than 10 or even less than minus 10 or even huge number. That is actually called as pre-logits. It's called as mathematically anything before a activation function is called as a logit. A single neuron is made up of a dot product, and after dot product, it is called a simple function on it, which is activation function. So going to TensorFlow Playground, you will find it has an activation function. So everything does a dot product, and there is a single function called as activation function. Okay, this is what gives us values. And before activation, it is called as logits, and post activation, it is whatever the value it is. So if you want to get value in probability, we use a softmax operation. It is a mathematical operation wherein whatever are the values given to it, we shuffle them in such a way that they are in a format of probability. I said TensorFlow is nothing but a glorified calculator. If you check the source code of what is softmax doing, you will find that it is calculating that maths operation. We can do log, we can do a lot of other functions. It's a glorified maths plus some automatic relationship finder, something in this TensorFlow library. Okay, so error value calculates the error. So what we do is, whatever is the model's prediction, which we calculated, and whatever is the actual prediction. So we learn from the data, right? So let's say for digit recognition, the fact that 3 looks like 3, we know the correct answer. So what we do is we ask the model to predict randomly based on random weights, and we simply then correct it because we know the right answer. Okay. So what we do is for every value we predict, and then we simply correct the all the parameters of the model so that error reduces. That is what the error minimization is. I know it is confusing, but try to visualize it, try to connect it as a neural network is multiple neurons. Each neuron has weights. Eventually, what we are doing is error minimization. What is the error dependent on? Error is dependent on incoming weights, right? And if we find relationship between in the weights and the error, we can tweak the weights to minimize the error. Ooh, where are hands? So as long as we find relationship between error and weights, we can tweak the weights. We adjust all the weights in such a way that error keeps on reducing. And when we find a combination where error is very close to zero, we have found the right answer. Okay. This is called as model training. A brute force way of finding combination of weights where our error is minimum. Okay. If you start training the code for the data set which we have taken, MNIST, you will find that it runs very quickly. Do it. Go to this code, simply change, instead of this tf.keras.data set, change this MNIST to CIFAR 10. What it gives us is a similar size data set, but it is changed from black and white to color, and the image size is 32 pixel by 32 pixel. It is not 32 megapixels, 32 pixels. That small. A 32 pixels into 32 pixels colored image, if we take such a small image, even for that, the learning, which is nothing but error minimization and finding the parameters for which the error is minimum, the learning of that, which is called as training, it takes a lot of time, even for 32 pixel by 32 pixel. So you could imagine how time consuming it would be for bigger images. So that is why, in the rest of the advanced lectures, you will find people store standard architectures, and they reuse the trained parameters which are trained by these big companies who have a lot of money. Okay. So in this lecture, we are not only looking at the architecture, we are also looking at what are the popular architectures. So if you hear these words, they are nothing but these architectures. So don't get demotivated here. If you're learning deep learning, these things demotivate you a lot. There are a lot of words being thrown at you. SqueezeNet, ResNet, ExceptionNet, AlexNet, GPT. It's just the name doesn't convey anything it is doing, and what it is doing is just a tiny bit changes to this standard neural network architecture. You will find these changes are very small, not that small, but for understanding purposes we can definitely see, as long as we know base model, then rest of the things kind of like remains the same, right? So that's all it is. All neural networks are this. And here, if you check in the candidate handbook, there are some parts here which is using pre-trained models, what is overfitting and this thing. Let's go to that part, and then our this entire unit 2 revision will be done. So a trained model is what is important. It is a value of a parameter which gives us a minimum error, right? So once we get a trained model, a learned model for which error is minimum, we can save those values, and that is model saving. So when you say model.save, those values are saved, and we can directly load these values here. If you want to find where are these models, two of the popular websites are Kaggle models. Google owns Kaggle. And Hugging Face, the currently most popular library where all most popular models are used. So this is such a amazing thing. These two libraries are most important, TIM and Transformers, because they have everything. Everything just in one line. You can, do it, get it, and start using it. So, Menasnet, MobileNet, NASNet. All you need to do is TIM, create model, and give the name, and you have that model available for use. Same for transformers. This library, you just, check whatever you want. And for that, what are all the list of models? This library has everything in one place. Okay, so instead of going here, you could also go to Hugging Face models, and you can see list of all the models for all the tasks in one place. So this is your entire deep learning field. Different models trained on different data sets, and learned models are hosted in this one place, Hugging Face or Kaggle models. Use the right one and improve upon it. Use the right one, use the which has existing knowledge and improve upon it. And that is what we call as transfer learning. Okay. So transfer learning is done, sharing model is done. The last part is overfitting and underfitting. Okay. Overfitting, remember, as you know, a topper who does just rote memorization, someone who has no understanding, just memorization. If a model was, if that person was personified, it would be a overfitted model. So what it has done is it has simply, it gets us very high marks. But when we actually start using it, it is useless. It gives us wrong values. So very high, very high performance in practice, but very low performance in real life. That is overfitting. Underfitting is, when you have not studied at all. This, you have not studied, not understood, nothing. So underfitting is when model is simpler than the task complexity. So what do we mean a complex model? A bigger model is a complex model. That's all it is. A bigger model is a complex model in more number of parameters. And when we increase the number of parameters, training time increases exponent not exponentially, but you will find it takes a lot of time to finish your training. So that's why our aim is find the smallest model which can train in a time which is affordable to us. Smallest model which can train in a time affordable to us, and that is the right model for us. So underfitting is when model is much simpler than the task complexity. Overfitting would be is model is much more complex than the task complexity. So then we simply reduce the model size and we should get a better accuracy. And a correctly fitting model is where complexity of the model and complexity of the task matches. So this is how conceptually you can connect everything. I have tried to connect this code, and I have tried to, write this code in smallest number of words as possible. So you'll find everything is very simple to write in code, and it is also very simple to immediately visualize. Use TensorFlow Playground, use NNSVG. Also go here and see what are the models and this thing. So by going through all of these things, you will learn all the essential things you need to build and train a neural network. Everything going forward is based on these fundamentals. So understand a single neuron, understand what these internal mechanisms are, end to end. And once that is done, you have mastered almost uh, end-to-end pipeline of neural network. So in lecture one, we saw the basics things and we built on it a tiny bit and we improved on it to such a level. So this and we'll build upon it further for computer vision and our natural language problems. Okay, so see you in the next lecture.